I wanted to thank you guys off the bat for joining us. My name is Rick Segrist, and I'm an account executive here with CAE, and calling in live from the Northwestern Mining Association show in Reno, Nevada. We also have Damian Gregory joining us from Toronto. So a little bit about Damian. Damian's Open Pit Solutions Manager here in our North America region, and he's stationed in in Toronto. He's got 15 years of practical experience, and over the past several years he's been working with CAE as a consultant, now the Open Pit Solutions Manager in charge of one of our newest products, which is SOPP, or Strategic Open Pit Planning, and it's a tool that utilizes the cloud to do sensitivity analysis and a lot of cool things. And actually, I'll let Damian get into it. So, Damian, go ahead and take it away. And
thanks, Rick. Welcome, everyone. The next minutes we'll go through a few slides, and after that I will show you a live demo with the application. CAE Mining has a broad range of products and solution offerings. They range from simulators, software, and consulting services. CAE Mining is currently developing Summit. This is the next generation of its geological and mine planning software. The initial development is focused on 4 main solution areas, such as strategic open pit planning, resource estimation, specifically conditional simulation, underground stope optimization, and geological database reporting. In the medium term, CAE Mining is striking balance between investing in existing products and new solutions on Summit. Summit is a web-based system that uses high-performance computing to deliver highly collaborative solutions that are not readily available on a workstation product. The reason to select these 4 solution areas is the fact that they either need this high computing power, or they exchange large volumes of data between multiple users to provide a collaborative environment. During the rest of the presentation, I will focus specifically on strategic open pit planning. Summit's strategic open pit planning is using high performance computing to do sensitivity analysis. This allows to quickly understand the primary economic driver of a project. In addition, with Summit, you can investigate the probability of achieving certain outcome from the deposit. Both sensitivity and simulation analysis can provide an insight into the project characteristics that cannot be obtained with any traditional workstation solutions in that time. This is because Summit uses high-performance, scalable computing power on the cloud. Sensitivity and simulation is nothing new, but is rarely carried out with sufficient degree of rigor during time to carry out the studies. Why? Because mine planners usually have limited time, a lot less than what it would be desired to perform all these studies. The computation times can be lengthy. It requires a long preparation and setup time to define the inputs for all these different scenarios that need to be run and analyzed. Because of manual process in a workstation, it is prone to user errors. To reduce time, we may not detect all project characteristics, and to a big extent relies on high degree of local data management and individual commitment, particularly when it comes to compiling the results from a few hundreds of different runs into one spreadsheet or document that can be easily analyzed and presented to the management. Desktop applications can produce individual results, but they are not the most suitable environment to perform this in an organized fashion. And CAE Summit is really delivering this to the mining industry. This slide summarizes the needs to compute many scenarios and the driver for us to develop CAE Summit. Summit provides mine engineers and management ability to be prepared in advance. Computing different scenarios and analyzing them before commodity prices go down or before the cost escalate gives competitive advantage to have the answers ready when the economic situation change. Usually such changes happen quick, and it is really nice to have the answers ready before we need to have the answer. And with using Summit, mining companies can be proactive. Why we need to run more and more scenarios? Because prices, cost, exchange rates can fluctuate. We have seen recent examples. In addition, we need to analyze different processing options, so we need to run multiple bit optimization for sensitivity and simulation. What we have achieved so far with CAE Summit. We can bring 2 weeks of work down to 6 hours. This is just one example where we show 90% time saving. In fact, CAE Summit has no limits. Depending on the needs, it can use more than 1,000 CPUs at the same time to compute many scenarios for multiple deposits. In addition, the available data storage is virtually unlimited, so you can decide how many deposits you can compute at the same time. Up to now, we can use bit optimization to do sensitivity analysis. We can use bit optimization, optimizing large Grossman bit for simulation risk analysis, and this is what I'll be showing you later today. Our plan is to continue adding new functions and have pushbacks and scheduling available on the same environment next year. A few words, what is sensitivity analysis? For example, we have 4 parameters that we want to analyze, and we run different bit optimizations, varying 1 parameter at a time. For example, I'm changing the mining cost, and we generate 9 different bits. Then we start changing the base metal price, and the mining cost is locked at its base case values, so we compute 8 more scenarios. In the same fashion, we continue changing the slope angles and the processing cost. So by varying these 4 parameters with 9 values each, we have 33 different ultimate bits to be computed and analyzed. This is a typical outcome from a sensitivity analysis study. We have a spider graph that in this case shows 8 parameters that have been analyzed. Note this is a web browser. I have logged on to this page on the internet where I define the inputs, I upload the data, and have the computations performed. Each dot on the spider graph represents generation of an ultimate bit. In our case, we have 58 bits, I believe. Each of these bits can run several hours, even days. Each bit has been generated by varying 1 parameter at a time. The key performance indicator that I show at this time is recovered gold. You can see on the right-hand side we have a list of quite a few KPIs that we can select from. The graph shows the change in recovered gold of the ultimate pit in response to changes in the input parameters that are shown on the legend. You can see the 8 parameters that have been used: copper price, unit cost, leach processing cost, average sinking rate, gold price, oxide processing cost, leach recovery for copper, and slope angle. If the line for parameter is steep, that means a small change in the input parameter value results in a relatively large change in the KPI. For example, we see on the screen that the blue line representing the gold price is a lot steeper than the orange line for the average sinking rate. And it's a little bit steeper than the line for copper price. If a line is nearly horizontal, that means this KPI is not very sensitive to changes in the input parameters. What we see on this spider graph is the fact that the line is not straight. A different section, the line changes with different steepness. What is common is that all these increments are the same. So on the horizontal, you see the increment change in percentage, and on the vertical, you see the percent change of the KPI. Changes in gold price and slope angles and mill processing costs have a much more significant impact on the recovered gold than leaching cost and recovery. You can see this also on the right bar chart, where it shows the overall relative impact of each of these 8 parameters that we have analyzed over the KPI, which is recovered gold. We can change these KPIs, and I'll show later during the live demo. This is a gold mine project. That's why it's expected that the gold price will have the most significant impact. And so we see that the leach processing cost is the least influential factor. This is particular for this specific deposit. In some other deposits, we'll be able to see that the average sinking rate doesn't bring any significant difference, or the slope angle, for example, doesn't affect to big extent the variation of the pits. In our case, our slope angle is one of the most significant factors. What is simulation analysis? It's very different from sensitivity. While in sensitivity, we vary one parameter at a time, and we provide the values from which to vary. With simulation analysis, we provide probability distribution for each variable that we want to analyze. What we see on the screen is the distribution for mining cost, for example. And we have probability of having 95 cents, that was 30%, probability to have a mining cost at $1, 15%, and so on. In similar fashion, we provide the distributions for mill processing cost and for mill recovery. Using these inputs, Summit is using Monte Carlo type of simulation to randomly select sets of inputs within the distribution that is provided. So instead of varying one parameter at a time, we vary all these 3 at the same time within the distribution, and the result is a similar frequency graph that is showing that out of 150 simulations that I have performed, 57 resulted in pits with net revenue between 650 million and 850 million. For example, you can see that this bar responded to corresponds to 28 pits in the 700 million bin, and this bar has 29 pits in the 800 million bin. It shows that the net revenue of the ultimate pit has a range from 300 million to 1.3 billion. An investment decision about capital allocation and at which pit to actually design are not always made taking into account this type of potential variation. So we can make a decision what is the most probable pit that we need to focus on for our future design work. When performing simulation analysis, it's important to use correlation. And this slide shows the historical data comparing three commodities like gold, silver, and copper. As you can see, in some periods, actually in most periods, they're quite closely correlated. In the last few years, we have seen some deviation from this. It's important to be able to correlate when performing simulations, because we don't want to analyze scenarios in which Monte Carlo selected high gold and low copper price, for example. So the correlation allows this to be taken care of in order to provide meaningful, reliable results. One of the most useful outputs from simulation analysis is the ability to analyze the statistics. With sufficient number of simulations, the probability of achieving certain outcomes can be investigated. In this example, we have three ranges of recovered gold and NPV. And we can see the respective probabilities. For example, I can say that with 90% probability, we will get a little bit over 20 million grams or 646,000 ounces from this deposit. You can also see that the probability of recovered gold between 20 million grams and 22.5 million grams is about 63%. Or the probability to have less than 20 million is 9%. And the probability to have above 22.5 million grams is 28%. We can change the KPI. For example, we can also see the NPV. So the probability of having NPV between 400 million and 700 million is 60.7%. And the probability to have NPV above 700 million is 10%. All computations are based on large Grossman optimization. So is the NPV that is calculated using a sequence following the LG phases. It is not the actual NPV for the project, but it gives us a relative point to compare between different scenarios. We know that when we schedule properly these pits, the deposit will have a lot different and a lot more practical NPV. This example, we change the range for the NPV, and now we can see that the probability of having NPV between 300 and 340 billion is 5%, and we have almost 90% probability to have NPV greater than 90%. What are the benefits of using CAE Summit? For the end user, we have well-known techniques that are now provided in modern computing environments. The same algorithms that are available in our desktop application NPV Scheduler. Some of those are already ported to CAE Summit, and that's exactly what we use to generate the optimized pits. The ability to use multiple CPUs allow quickly to perform all these different optimizations in parallel to reduce the time to perform sensitivity and simulation analysis. And as I mentioned earlier, the time reduction comes not only from the computation, it also significantly reduces the time to compile the results and present them in a format that is easy to analyze and understand. In a few minutes, I'll start the live demonstration and we'll be able to see this. This is the most practical way to understand the economical and geotechnical risks. It's also the most cost-effective way. Because it is available via web browser, it allows engineers to work anywhere, anytime, and my managers can log on to the system and see the results and analyze the outcomes at any time where they connect to internet. For the IT department, this is reducing drastically the uptime. There's no software to deploy or install. You need the proper credentials to log to the appropriate web page, and depending on your permissions, you can have access to the information that you're allowed to access. The system is very scalable and provides just enough computers that are required to perform certain tasks, and these computers are being released later when no computation is pending, so don't pay for the time where these computers are not utilized. Overall, this is reducing the IT costs and this is reducing the cost to perform studies. Now I will switch to the application and show you how we are actually achieving this. For those of you that are familiar with MPV Scheduler, our strategic open pit planning application, you see nothing new in terms of functions, just different interface to provide the inputs. In a very similar way, we're providing the economic parameters, for example, just different interface to provide the same type of inputs. So that's how we define the prices, recoveries, mining cost, processing cost, and so on. In a similar fashion, we provide the ultimate pit settings, so we decide what optimization algorithm to use. For example, I have selected large Grossman to optimize the pit. I decide on the sequencing factors. I can select if I want to use pit limits. I have certain pit limits with obstacle removal costs or exclusion zones that I can use. I can use different slope regions, and I can provide different slope angles or different azimuths. And the most interesting part is the way we can quickly define the sensitivity parameters. Here we see the list of all possible parameters that can be used for sensitivity analysis. This is most economic parameters and some of the important ultimate pit parameters. For example, I have selected to run sensitivity analysis on gold price, copper price, unit cost. I think I have also selected new processing cost, leach processing cost, sinking rate, and slope angle. So from this parameters that I have selected, here we see the variations that I want to use. My base case value for copper is $4,600 per ton, and I want to investigate how my pits will respond to copper price changes that range from $3,400 to $5,800 per ton. In a similar way, I changed the unit cost, which has base value of 250. And now there is with increment of 20 cents. Similar to leach processing cost, average sinking rate. I want to see what my pit will be if I sink 2, 3, 4, or 8 benches per year. For gold price, I selected to run at increments of $5 per gram, starting from 45, having 3 increments above and below. So this is how I quickly define all these 58 or 60 different scenarios to run. And I'll show you quickly the result from computing all this sensitivity runs. In this page, we can see the relative impacts of several KPIs. I can select up to 6 to be displayed at the same time. And we can see how they interact with each other. I can have the sensitivity graphs for all of these KPIs. Some of those follow the same trend, but they can be quite different. In addition, I can select to view one parameter at a time. I'll select from the list. For example, this is the distribution of the revenue, or this is the distribution of the recovered gold, what I showed in the PowerPoint presentation earlier. So this is the response of recovered gold in the ultimate pit when we vary each of these 8 parameters at the increment that we saw a little bit earlier. Each line represents one of these parameters. For example, this is the blue line for gold price. This is the line for the copper price. So you can see it's not straight line, and the behavior is different at different parts. Here we see that our recovered gold is decreasing a lot quickly, then increasing with the same increments. I always use the same increments of $5 a gram in both ends, but we see quite rapid change on the left-hand side and not so quite increase on the right-hand side. We can analyze each of these parameters. On the right-hand side, we see the relative impact. And we can quickly change the KPI. And here is the resulting spider graph for total mass in the pit. Something that you may not expect. You can see how the slope angle is changing the total mass of the pit. It's quite unusual, but we can focus our attention and investigate why this is happening. As I mentioned earlier, each dot here represents one large Grossman pit optimization, and some of those may take hours. Well, the beauty of Summit is the ability to compute all this in parallel, so we can do 50, 100, even 1,000 if we want to. I'll now go into simulation analysis, how we provide the input for simulation. We have the same list of inputs that we can investigate. You can see them on the left. And I selected gold price, copper price, and mining costs for the purpose of simulation analysis. I have decided to compute 150 simulations and I provide the distribution for each of these three parameters. For example, gold price and copper price I defined with normal distribution. For gold price I have mean 45 and standard deviation 7. I can optionally select the minimum. I don't want to analyze any bits where the price would be less than $20 per gram. For mining costs, I selected to use triangular distribution. As I mentioned earlier, we can use correlation, and I have selected correlation between gold and copper to be 0.6. So that's all we need to do as far as it comes for inputs. Now I'll show the results. So we already saw this, the simulation. We see the histograms of the inputs. So we are inputting the distribution, and then Monte Carlo selected to use the distribution and provided these inputs for our analysis. For 150 simulation runs, it picked 25 times copper price between $43 and $4,700 per ton, and only 5 times it selected price between $59 and $6,300 per ton. We can see the distribution of the inputs. In addition, we can see the distribution of the outputs, the KPIs, and I'll select the recovered gold, for example. As you can see, the frequencies is quite skewed, and this frequencies is quite different from net value, for example, or total mass in the pit. I'll now switch to a different type of report to show the simulation data. We can download the results from Summit. We have export function that will allow us to export all computations runs that have been delivered. You'll see in a few seconds a table that contains all simulation results. This table can be exported to a CSV file for further analysis and for safekeeping to come later. Don't need to use the system at all times. You can use it to compute the results, download the results that are required, and you no longer incur cost of using the system. So what you see here on the first line is the base values of the inputs and the corresponding KPI values. And from line 2 on, you can see the simulated values. First 3 columns are the simulated inputs, and all the additional columns are the resulting KPI values for each of the simulation runs. In addition to the table with the results, we can also see the statistics that I showed you earlier in the presentation. And the statistics allows us to interactively enter probabilities and see the outcome for the corresponding probability. Now I need to wait to refresh my page. I'll go back to my study and will display the report that I wanted to display. while we're waiting, we can open the conversation. I can answer questions because we are getting to our Q&A time.
Yeah, so we had a couple of questions come in, and again, feel free to type in questions during this time, and we'll have Damian, the product expert, answer those questions. But one of the questions we got was about the security. Basically, we were curious how secure this web-based application was in using the cloud.
This is very secure environment. We are using Microsoft Azure cloud. Microsoft is the provider, and as provider, they ensure that the data is backed up. It's transferred through secure web connections using the same encryptions that are being used for banking transactions, for example. Because Microsoft is dealing with data centers all over the world, it has to meet all security requirements for all jurisdictions where it operates. So it is very secure.
Okay. One of the questions we got was based on the fact that it is web-based. Are you able to use tablets or really any sort of window to the internet? Can you connect?
We can use. We can access Summit to any hardware that supports Microsoft Silverlight. This is not available on iPhone or iPad, for example, due to hardware limitation imposed by Apple. But you can use it on MacBook, for example. You can use it on any Windows-based operating system. You can use on Samsung Galaxy and Microsoft tablet, for example. I'm using my computer as a monitor only at this time, and all the computations are being done somewhere in the world. And I get the results back. So I'm not using my computer for anything else, just as a web browser.
Okay. One of the questions that came in was, how is syncing rate applied?
The syncing rate is applied. I'll show you. We have option in Entity Scheduler, and as a result, this function came into Summit. When creating a large Grossman pit, we can apply top-down bench discounting. For example, I have discounting rate defined at 10% per year, and with average syncing rate of 5 benches per year. It means I'm discounting the value for each bench by 2%. So by discounting the value, the economic value for each block for each bench, depending on the depth of the where it stands, I make a pit using this discounted value. This is optional. I can use it or not. So when calculating the pit, we will use different discounting. When I change the syncing rate to 8, for example, then we will be applying 1.25% discounting for each bench. This is how we can use the average syncing rate that implies how quickly we can sync. When making pictures, we don't know how quickly we're going to mine this deposit because we don't know how big deposit is to start with. But we can have some preliminary input as to how fast we can sync. This is iterative process, and first parts we will not use discounting, but after that we can start using discounting after we know how big our pit is and how quick we can mine it.
Okay, perfect. All right, and that looks like it was it for questions, Damian. So what I'll do is I'll follow up with you individually and send you a copy of the link to the presentation. And feel free to join us next week. We'll be talking about QA/QC with Baha Gurgis, one of our consultants here in North America. And thanks again for your time. I look forward to hopefully speaking with you all soon. Thanks, everybody.